Okay, hi everyone, and welcome to the March MAPP webinar. Thank you for joining today. It's good to see everybody on the line. Today's topic is on the stratosphere. We're going to explore a number of different elements of modeling work that's going on, targeting stratosphere and stratosphere-troposphere relationship. And we're going to hear first from Larry Horowitz, who is at NOAA GFDL, and he's going to discuss some of the modeling efforts there, focusing on the chemistry and the dynamics and tropospheric coupling. And then we'll hear second from Judith Perlwitz, who's out at NOAA Israel. And she's going to talk a little bit more about the coupling and look at CMIP 5 models. One of the plots that's cycling on the screen right now is from a paper that Judith was involved with, looking at the CMIP 5 models, if you've noticed that. And then finally, we will hear from Ming Kai, who is at Florida State, and Ming is going to talk a little bit more about predictability, basically building on the stratosphere-troposphere connections. So it's kind of a nice flow to today's webinar, and I really am very appreciative of these three individuals joining today. So thank you each for taking the time to present. The format of these webinars, as I mentioned, we have 3 talks, and between the talks, we will hopefully have time for questions from those on the line or anybody who's in the room here. And if you have a question, there's a hand raise feature in WebEx, which I encourage you to use to indicate that you have a question. I have a slide up on the screen right now which gives some instructions on how to do it. Basically, at the top of your screen, you should see a bar that says Viewing Climate Program Office, and if you put your cursor over that, a window will pop down. You want to click the Participants button, and then this window will pop up, and at the bottom left, there's a little hand feature, and if you click that, it'll let me know that you have a question. I can unmute your line, and then you can ask your question, have a discussion with the speaker. So we do this just to try to control any noise on the line during the webinar. So without wasting any more time, I want to turn it over to Larry Horowitz. Larry, are you on the line?
Yes, I am.
Sorry, we're muting each other. Sorry. Okay, so Larry, I'm going to transfer control over to your computer right now.
Okay.
And then just share your desktop with us. And
yep, I think we're good.
Yeah, it looks good. Okay, great, Larry. Whenever you're ready, go ahead.
All right. Thanks, Dan. Today I'm going to be talking about several different projects that we've been doing on modeling the stratosphere here at GFDL. Talk about chemistry, a little piece about dynamics, and some of the coupling between the stratosphere and the troposphere. My co-authors on this work are Mayun Lin and Pu Lin at the Cooperative Institute at Princeton, and S.J. Lin and Lucas Harris here at GFDL. I'm grateful for Lucas so that I don't have to be the only non-Lin on this presentation. It's just a coincidence. So I'm going to be talking about some work we've done in several different modeling frameworks. One of the main models I'll focus on is our AM3 atmospheric model that we used as part of our coupled model CM3 for our CMIP 5 simulations. And this model includes both tropospheric and stratospheric chemistry, fairly complete representation. It has a parameterization for the source of halogens in the stratosphere, but the chemistry is seamless throughout the troposphere and stratosphere, a consistent set of tracers, and they are coupled with the radiation and dynamics in the model. The model is formulated on a cubed sphere dynamical grid, finite volume grid, developed by Putman and Lin. And the resolution that I'll be talking about initially is a 200-kilometer resolution. Now, we designed this model to study issues including chemistry climate feedbacks, and for the purposes of this talk, I'll focus on the stratosphere-troposphere coupling, both in terms of chemistry and dynamics. So first, a couple of examples of our simulation of chemistry of the stratosphere. These are a couple of figures. The left column shows the total ozone column seasonal cycle as observed by the TOMS satellite instrument and as simulated by our CM3 coupled climate model. And we can see that CM3 simulates the main features of the geographic and temporal variability of ozone column, low values in the tropics, high values at mid to high latitudes, including the development of the ozone hole here in the southern hemisphere over Antarctica in the austral spring. The right panel shows the time evolution of the ozone hole, of the Antarctic ozone hole, showing the October mean ozone column in observations in black lines and symbols, and those spaghetti lines in color are various models that participated in CMIP 5, including here in dark green, the GFDL CM3 model. And we can see that we capture both the trend, the development over the past several decades of the ozone hole, its stabilization in recent decades, as well as a reasonable representation of interannual variability. So we used this model to study, among other things, the impact of volcanic eruptions on stratospheric climate and chemistry. On the left here, we see the ozone column, the global ozone column response to volcanic eruptions, and we find varying responses that depend on the chemical regime of the stratosphere, in particular the halogen loading levels. So in the recent volcanic eruptions, El Chichon and Mount Pinatubo, where we have high halogens in the stratosphere, we get a depletion following the volcanic eruptions, and the surface areas increased surface areas allow more chlorine to be activated. Whereas earlier in the record, when we have low chlorine, we actually see an increase in stratospheric ozone in response to the volcanic injections and the increased surface areas, reflecting different catalytic cycles responding in a low chlorine stratosphere. On the right-hand panel here, we see the temperature response to volcanic eruptions, punctuated warmings following the volcanic eruptions because of absorption of solar radiation by the volcanic aerosols. And those warming signals that match observations from radiosondes and satellite instruments are superimposed on a long-term cooling trend in the stratosphere, and that's a result of both increased CO2 concentrations and of ozone depletion. So now moving down a little bit to tropospheric coupling, since we have this model that credibly simulates stratospheric ozone, we can look at coupling of stratospheric ozone down into the troposphere. And so this work, led by Mei-Yun Lin, looks at an ozone intrusion from the stratosphere reaching down into the troposphere, shown here on a cross-section from northwest to southeast over California in May of 2010. And we can see high ozone air descending essentially isentropically from northwest to southeast and reaching the lower troposphere over Southern California. This was done with a high-resolution version of the same AM3 model. This is using a 50-kilometer resolution version, but still with full stratospheric and tropospheric coupling, and this time nudged to GFS winds to get the correct synoptic representation for this time period. This event took place during the NOAA CalNex field campaign over California during 2010, so we have plentiful observations with which to compare and evaluate the simulation of this ozone intrusion in the model. So here we use a network of daily ozone sondes stretching from Northern California to Southern California during this period. We can see in the left panel those ozone sondes from this particular day, May 28th, strung together from north to south, showing this descent of ozone from north to south, reaching down into the lower troposphere, about 4 kilometers, and below in Southern California. The rightmost panel shows a coarse resolution version of AM3, a 200-kilometer resolution, and it has a hint of that same signal. But then when we move to the higher resolution, that picture sharpens up quite a bit, and we get a fairly good representation of the dynamics of this event. And so that's a benefit of having coupled ozone chemistry running through the stratosphere down to the troposphere, that we can actually simulate the dynamics and chemistry in a coupled way of these ozone incursions from the stratosphere into the troposphere. We can look at a broader context of this event, and we see that the following day, May 29th, there's a widespread high ozone episode observed over the southwest United States during that time period. And our model attributes a lot of that ozone enhancement to ozone transported down from the stratosphere, as indicated by a tag tracer in our model. So we find that stratospheric sources can periodically or episodically contribute to high ozone events over the southwest United States during springtime, causing total ozone to exceed the health-based air quality thresholds. So we also find that the amount of stratospheric ozone reaching the surface over the western U.S. varies considerably from year to year. Here we have observations and model simulation of total ozone. Observations are in black, model is in red, showing year-to-year variations of April to May ozone average over the western United States. And we capture a lot of the variability observed from year to year. And our model attributes that variability to changes in the amount of stratospheric ozone reaching these surface sites over the western United States. In particular, we find that in springs following La Niña events that winter, we find elevated ozone concentrations and elevated stratospheric contributions. These are indicated by the blue arrows on the top, the La Niña events where we see high ozone concentrations and high stratospheric contributions. And Mayun has attributed this to the dynamics occurring during La Niña winters and springs, during which the jet stream has a very wave-like feature that promotes more cyclone passages and cold front passages and more tropopause folding events, bringing stratospheric ozone deep into the troposphere and extending, in many cases, down to the surface. So we believe that this correlation with La Niña winters may provide some degree of predictability of ozone. Knowing that it's a La Niña winter, we may have some predictability of air quality exceedances that following spring over the western United States. Moving on from ozone transport down into the troposphere, back up into the stratosphere, and looking now at dynamics, this is work that was led by Pu Lin, and this is looking at the stratospheric overturning circulation known as the Brewer-Dobson circulation. And she classifies the strength of the Brewer-Dobson circulation in two branches, a shallow branch of air crossing through 70 hectopascals and extending up to 30 hectopascals, as well as a deep branch of air that's circulating above 30 hectopascals. And this table on the right shows that our model, CM3, matches fairly well what the ERA interim reanalysis shows for the strength of the Brewer-Dobson circulation, particularly for the shallow branches where we get almost exactly the same strength of the overturning circulation as the reanalysis. So that was the climatology. We also find that the strength of the Brewer-Dobson circulation varies from year to year and has longer frequency variations extending out to decadal and multi-decadal variations. So these points each show a period from an unforced control, a 1700-year unforced control run. And we see that there's some variation on the y-axis in the mass flux, both in the shallow branch on the left and the deep branch on the right. And the left-hand plot shows that these variations in shallow Brewer-Dobson circulation strength are correlated with delta TT, which is the tropical surface temperatures in our model. So variations in tropical surface temperature are correlated with the strength of the Brewer-Dobson circulation in this unforced control run, whereas in the deep branch, it's not particularly correlated. It's very weakly correlated. So these are unforced variabilities. We can also look at historical simulations in our model where there's forced variabilities due to greenhouse gases and other forcing agents changing. And there we can see we get bigger changes in tropical surface temperatures as well as larger changes in the Brewer-Dobson circulation strength, but the correlation looks very similar to the unforced variations found in the control run. We can look further at other simulations with our CM3 model, including natural forcings only, anthropogenic forcings only, aerosols, and greenhouse gases, and find that in all cases, the shallow branch of the Brewer-Dobson circulation shows a very similar correlation with tropical surface temperatures for forced and unforced variabilities. And this was looking at decadal to multi-decadal variations. If we look at year-to-year variations, we actually see a very similar picture, very similar correlation. We can evaluate that interannual variability by comparing, again, with the ERA interim reanalysis. So on the left, we show the reanalysis. On the right, we show results from an AM3 simulation forced with observed sea surface temperatures. And we find that for the shallow branch, the correlation between lower tropospheric surface temperatures and shallow Brewer-Dobson circulation strength is well simulated by AM3. So the mechanism that Pu Lin has come up with to explain this phenomenon is that we start with a surface warming over the tropics. That's connected to the upper troposphere by the moist adiabatic lapse rate, so we get an amplified warming in the upper troposphere. That increased warming in the upper troposphere establishes a larger meridional temperature gradient, which leads to accelerated subtropical jets. And that acceleration of the subtropical jet moves the critical line for wave absorption in a way that causes more wave absorption in the lower stratosphere, and that leads to an acceleration of the Brewer-Dobson circulation in the model. So this links lower tropospheric warming in the tropics to the strength of the stratospheric overturning circulation. The final set of results I want to show is led by S.J. Lin and Lucas Harris, and this is looking at dynamics of the stratosphere, in particular focusing on the QBO. So this is an example showing the NASA MERA reanalysis, showing what the QBO looks like. This is the zonal wind plotted along the equator. And you can see alternating westerlies and easterlies descending through the stratosphere to a level of about 50 hectopascals. This phenomenon is typically very difficult to simulate in GCMs, but it's an important aspect of the stratospheric circulation, impacting sudden warming, stratospheric ozone, and possibly even tropospheric weather such as hurricanes and winter storms. So we would like to be able to simulate it in our model. These results are now using a different model called HIRAM. This is a higher resolution model, atmospheric model. If we just run this model as a free-running GCM, it doesn't show any signs of a QBO. If we try instead initializing it with the state of the MERA reanalysis, we find that it can initiate a QBO, but it has about one cycle of QBO and then it peters out very quickly. So these results so far have been using the standard hydrostatic version of the dynamical core, that is the same version that we use in the AM3 model. SJ and Lucas have also developed a non-hydrostatic version of this model. The results are shown on the right here. If we initialize this model the same way and run it with a non-hydrostatic option in the dynamical core, we can see that it develops, sustains a QBO signal with approximately the right amplitude and period, and it extends maybe not quite deep enough down into the stratosphere, but it does. There's still some signal of it down to about 50 hectopascals, so it's doing fairly well. We believe that this improved simulation of the QBO in the non-hydrostatic dynamical core is, at least in part, a result of better simulation of Kelvin waves in that version of the model. This improved simulation of QBO may also provide some enhanced predictability for tropospheric weather insofar as the QBO is coupled to phenomena like hurricanes and winter storms. So to wrap up, we've shown that AM3 and its coupled version CM3 can simulate the major features of stratospheric climate and ozone, as well as trends and variability. We've shown that the response of ozone to volcanic eruptions depends strongly on the chemical regime, in particular the degree of halogen loading in the stratosphere. Mayer and Lin's work has shown that deep stratospheric intrusions can elevate surface ozone, particularly during springtime over the western U.S. and in years following strong La Niña events. We've shown that the tropical surface temperatures are strongly correlated with the strength of the lower branch of the Brewer-Dobson circulation, and that's achieved through modulation of wave forcing. And finally, the non-hydrostatic option of the cube sphere dynamical core allows us to greatly improve our simulation of QBO in our atmospheric models. Thank you.
Great, thanks a lot, Larry. So if you're logged in online, please use the hand raise feature to ask a question. I'll unmute your line. Any questions here in the room? So Larry, while we wait to see if anybody raises their hand, I'm wondering if you can comment briefly on some of the elements of the model, the coupled system, and the atmosphere that you're targeting in the next phase of GFDL model development cycle to do better with the stratosphere.
So we have an active model development effort underway now. The atmospheric model development now is being led by Chris Golaz and Ming Zhao here. And they are focusing on moving to higher resolution, focusing on improving the representation of convection and clouds in the model. And we do hope to have a version for our CMIP 6 simulations that does include similar complexity of stratosphere chemistry and stratosphere-troposphere coupling as we had in CM3.
Great, thanks. So I haven't seen any hands raised online, so I think we'll move to the next speaker. Larry, thank you so much.
Okay, thanks.
Okay, next up is Judith Perlwitz. Judith, are you on the line?
I'm on the line. Can you hear me?
Okay, great. Yeah, we can hear you. I just transferred control over your computer, so share your desktop with us. Great.
So are we at the first slide?
Yeah, looks good. Whenever you're ready, go ahead, Judith.
Thank you. So thanks, Dan, for giving me the opportunity to talk and present some results of my work with Tiffany Shaw. So what I'm going to do today, I'll try to give a brief overview of representation of dynamic troposphere-stratosphere coupling in CMIP 5 models, but I will focus on work that I've done in collaboration with Tiffany Shaw, who is now at University of Chicago. So I start with some general comments about troposphere-stratosphere coupling. First of all, that's been for a long time and has been assumed that this coupling is one way from the troposphere to the stratosphere. But during recent decades, since the 1990s, has been found out that this coupling is two-way, but still with the upward influence or the influence from the troposphere to the stratosphere dominating, and this coupling occurs mostly due to the upward propagation of planetary waves into the stratosphere and the interaction of these waves with the stratospheric mean flow. So these waves are generated in the troposphere by land-sea contrast and mostly by orography, and you see the impact on the stratospheric climatology clearly on the figures that I show on the right-hand side, which shows the winter-time climatology of temperature at 50 hectopascal, while in the southern hemisphere or over Antarctica, you have a very cold polar vortex. It's very circumpolar. In the northern hemisphere, the temperature climatologically, the cold temperature are much smaller, it's much less cold, and the vortex is shifted off the pole because of a strong climatological contribution of planetary waves. So this is due to the troposphere, due to the fact that we have in the northern hemisphere more planetary wave sources due to orography and land-sea contrast. The next slide, I put together a whole list of mechanisms that has been put down for a potential influence, downward influence from the stratosphere to modulate the tropospheric circulation. So still the source of any coupling comes from the troposphere, but they are under specific conditions, the stratosphere, specific mechanisms, the stratosphere is modulating these impacts. I don't want to go through all of the mechanisms. I'm sure it's not all complete. Lots of work you can see has been done in recent years. And we just want to point out one behavior is the wave reflection, which is work that I have done in the past with Niña and Tiffany Shaw. That waves are propagating in the stratosphere get reflected and move and propagate back down where they modify the tropospheric wave source. But the main point I want to make, and it's on the bottom and in blue, that Boville already showed in '84 that a degraded representation of stratospheric processes in AGCMs affects the simulated tropospheric mean climate and also its variability. So it's been suggested a long time, and now with the new CMIP 5 ensemble, which has a large number of high-top models, which have represented this variable stratosphere for the first time, we can actually do these grand ensemble comparison between height and low-top models, or models to understand, okay, does it matter and what is the impact in these models that are used for long-term, for climate and climate simulations and for the future projections on that, what the stratosphere actually means in these kind of models. So there I go quickly over these main findings of a couple of papers. First of all, I want to point out Charlton, Paris, and co-authors 2013 study on the lack of stratospheric dynamical variability in low-top versions of the CMIP 5 models. And what they found is, and you can look up that paper, is that especially in low-top models ensemble, the vortex, the variability is very weak on the daily to interannual time scale, much weaker than in high-top models, which are more consistent with observations. And the frequency of major sudden warmings is strongly reduced, and that affects the northern annular mode events in the troposphere. They are less persistent and leading to a shorter life tropospheric impact than in observations. Then there is another study by Lee and Black, 2014, on the structure and dynamics of the stratospheric northern annular mode in CMIP simulations. They in general confirm the findings of Charles and Paris for the stratosphere, that compared to high-top models, the low-top models generally underestimate the variability of the annular mode in the stratosphere, which is consistent with the weaker polar vortex variability. So, but when they looked at the ground ensemble comparison and the variability in the tropospheric structure of the annular mode, they didn't find much differences, and they found in generally a close consistency with the troposphere. So in general, you can't really distinguish if you in the tropospheric variability if you have high top or low top model. And then this is our study, and I want to talk a little bit more about the results. It's by Shaw, Perlwitz, and Weiner. It came out in 2013 in Journal of Geophysical Research, and we looked at the troposphere-stratosphere coupling linking to the North Atlantic weather and climate, including the representation of CMIP models. We introduced a new framework, so consistent with trying to do a process-oriented analysis that has been put forward as a NOAA, for example, for NOAA in their new MAPP proposals framework. We introduced a new framework for model evaluation of wave coupling between the troposphere and stratosphere based on heat flux extremes in the lower stratosphere. We did not do a pre-selection of low-top and versus high-top model. We really focused on how do they represent these processes in the stratosphere. And the main take-home message, I put it here already, is that a simple comparison between low and high-top models is not sufficient to understand structural tropospheric climate biases related to stratospheric representation in climate models. So I want to give a little bit more details on this in the study. What I'm showing here first is the January, February, March polar cap heat flux distribution at 50 hectopascal in era 50 interims. On the left, you see the climatology of heat flux in the northern hemisphere for 20 to 90 north versus pressure level, and you see that on average on climatology the heat flux is positive. So that means it's poleward, indicating that and generally in this time period you have upward propagation of planetary waves into the stratosphere. And so on the right-hand side, then we show the daily distribution of these heat flux values from January, February to March. And in red is the 10%, the 90 percentile of these values, indicating extreme positive heat fluxes means that we have increased, enhanced upward propagation, so suggesting that during these times you have a strong influence from the troposphere on the stratosphere by planetary wave propagation. The negative extremes you get, so they are not always positive. You have extremes which are on the negative side. That means that these values are negative, and they are indicating of downward propagation and wave reflection. So we have in this region, so for negative values, we actually simulate or find and potentially an influence from the stratosphere on the troposphere due to reflective fraction of these upward propagating waves back onto the troposphere. And I want to give you next a little indication how this influence looks like in the troposphere. So I start with showing the stratospheric life cycle for extreme negative heat flux values, which is based on a paper by Shaw and Perlwitz, 2013. So we looked at composites for these negative heat flux values, and we have looked at the onset period versus the mature period where you have these negative values. On the left side, I show the latitude height cross sections of the heat flux values, and during onset they are all positive, so it means you have upward propagation, and then during the mature phase you have negative heat flux values north of 60 degrees north, all the way down from, from the mid-troposphere to up to 10 hectopascal. So on the right-hand side, you can see what's the influence on the structure of planetary waves. I'm showing the on 70 degrees north longitude height section of the composite of the structure, and you can see that in the onset phase you have indicated in red, you have westward phase tilt, so it indicates upward propagation. But you can see that there's a dramatic shift in the structure of planetary waves to the mature phase. You have eastwards eastward phase tilt, and due to the strong change in the wave structure in the mid to upper troposphere all the way down to the lower stratosphere compared to the onset period. What does it, it's this impact on this tropospheric wave structure. So for this I show the composites, and on the left is the climatology, in black lines are the troposphere. So you have a hint at high latitudes of a wave 1. But during the negative phase, this wave 1 structure is strongly enhanced, and you can see the pronounced eastward phase tilt compared to 10 hectopascal, suggesting clearly of a downward propagating wave during this period. The next slide shows composites now. What does it mean for the troposphere? First of all, if you look at the total, not just wave 1, but at the total composite of eddies, so that we remove the zonal mean, you get the signature that is shown in the wave 1 is strongly recovered. So the influence is mostly due to the wave 1 impact. If you look at the 500 hectopascal zonal wind, it's the climatology is the isoline, and in color are the anomalies. You see a strengthening and poleward shift of the jet over the tropospheric jet over the North Atlantic, and even at the surface you see a strong impact on sea level pressure. Again, this is consistent with a positive phase on the NAO. So what I'm doing next is, in the second part of my talk, is how do models represent these wave coupling? And we look at here a histogram of positive extremes versus negative extremes in a large number of models. And the bottom, on the bottom is the positive extremes, and 10 hectopascal, 10% is the value of the error interim. So we show values compared to the error interim extremes. Values on the right side indicate you have more positive extremes in your distribution relative to error interim, versus on the left you have next. The same is for the y-axis. Positive, means you have more downward reflection, versus if you go below 10, you have less negative heat flux values. And if you see in general, if you compare, so they are on a straight line, so indicating that models that have, having low positive heat flux extremes also have low negative heat flux extremes. This is consistent with the fact that in models that don't propagate into the stratosphere, waves, they also cannot have a strong reflection. So that is kind of a strong connection. But in general, you can see that models underrepresent negative heat fluxes. Heat flux values. The most, compared to error interim, most of the models underrepresent this downward influence due to on the stratosphere to some extent. So what I'm comparing now, for the rest of my talk, I look at this, compare small bias models versus a subsample of models that exhibit a large bias in this representation of extreme heat fluxes. And I run through these quite quickly. So on the top, I show the grant ensemble of the PDFs. For the error is in black, and the small bias distribution is in blue, and red is the large bias. And you can see where there's a close resemblance in the PDFs or the histograms of error interim versus the small bias. While the large bias, you can see you really underestimate extreme large negative heat flux values. You have an enhanced occurrence of low positive heat flux values, so this is very pronounced. And here and on the bottom, I show the composites or the histograms for the small bias versus the large bias, and you can see the small bias ensemble are mostly high top models, except the Canadian model, and 3 of these low bias models are all the Max Planck model. So this is essentially the same model but different representation, I guess, from other stuff in the troposphere. So, and on the other hand, the large top models, the large bias are all low top models. So they are all low top models, but in general, it's not a full representation of all low top models, which are extreme. So here you compare what is the link to the structure and the troposphere between the climatology and the wave 1. So on the top right, I show again the era interim climatology. On the left, I show the small bias. In the middle, the large bias, and on the right, the difference. And you can see there's this much stronger resemblance of the planetary wave 1 structure in era interim and the small bias than in the large bias. You really underestimate the wave 1 amplitude at high latitudes in a climatological sense. This bias is not just in wave 1. You can get it also in the total wave structure, and you can see the small bias. We have, for example, you have a larger trough in heights west of Greenland, around the Hudson Bay, while this feature is very much underrepresented in the climatology of the large bias model. And in general, you reproduce this wave 1 structure bias, which I shown before because to show it briefly in the wave 1 field. This bias is also closely linked to to the simulation of the Atlantic jet stream structure. So in you can see that in the small bias, the jet relative to the large bias is seen as a difference. You have a poleward shift and hence strengthening of the jet. Consistent. This picture is consistent with the anomaly picture of era interim. If you look at the large negative heat flux composite versus climatology. So it becomes even clearer if you compare all these the daily zonal wind data over the North Atlantic in mid-latitudes between era interim, the small bias, and the large bias ensemble. So this is the daily histogram, and you can see while you have this close similarity between era and the small bias, but the large bias models really have a stronger occurrence of very small winds with daily wind values, which is much larger than what we find in era interim as well as in the small bias ensemble. So these are all data we compared from between 1979 and 2005. So that's the period we actually looked at. And finally, I show. So before we just looked at models and you'd have these grand ensembles, but these issues can be also related to, a sample of opportunities, and we try to reduce that by comparing models in the same model family, like the GFDL, the CM3. We said the small bias versus the large bias version for the heat flux is the GFDL ESM2, and the same for the Hadley Center model. We have the high top model HEDGEM2 CC versus HEDGEM CM3, which is a low top model. And again, you get the same feature that the structure of height wave 1 is much better represented in these small bias models, and which have this bias in the stratosphere versus the troposphere. And finally, but it's not just the stratosphere that matters, but also so the high top versus low top, but how you treat the stratosphere even in the low top models, and you can get very different results. So I show you a couple of examples for models that actually have a very, very strong amplitude of wave 1 at higher latitudes between 60 and 90 and 80 north. And this wave 1 has very little phase tilt to the wave 1 in the stratosphere. So, and what happens in these models is that there's a very, very strong interaction with the modelet, which leads to very strong reflection from the modelet that causes this structure. So you have in these models a very, very different structure than in these low bias models that I showed before. So I'm now at my summary. CMIP models that do not properly represent the distribution of extreme stratospheric heat flux exhibit the biased climatological planetary wave structure in the northern hemisphere. This is consistent with previous studies, and it's greatly reproduced by the CMIP analysis that we have done. And models that do the stratosphere well, that really are able to deal with the tropospheric wave forcing properly, the way how they related to their basic stage and allowing to develop reflective surfaces and so on, lead to a more accurate planetary wave structure and Atlantic jet stream position in the troposphere. Models without the proper presentation of stratospheric dynamics may be missing amplifying effects, both for the negative NAO, that is the sudden warmings, if they don't do sudden warmings very well, as well as positive NAO extremes due to the presentation of reflective surfaces or downward reflection. What did I try to say? Yeah, so these have, both of these mechanisms affect the NAO and causing, maybe not properly representation of the NAO in the troposphere and its variability. But I also try to make sure to explain that a simple comparison between low and high top models is not sufficient for understanding the structural tropospheric climate biases related to the stratosphere. So you can have if you strongly absorb your wave propagation signal, you underestimate the downward coupling. If you allow the waves to get reflected from the modelet, you really enhance your coupling to the troposphere. So which is both based on the fact that you do not represent stratospheric process as well. But having a higher modelet is still not a guarantee for doing this properly. So you have to a little bit more work to get that right. I think that's it.
Okay, hello? Great. Thanks. Hi, Judith. Thank you so much. That was great. So if there are any questions from the audience, please put your hand up. Yeah, I see one question already. So Judith, you have a question from Craig Long. Craig, are you on the line?
Yeah, here I am.
Okay, great. Go ahead with your question.
Yeah, Judith, did vertical resolution have anything to do with how well these models performed?
So I don't know. So it's I think it's. You mean for I think it's not enough to have the proper resolution. You also need to know what you do with the, if you have a proper representation of stratospheric wave drag, if you include that in the model or not, or if you only have aerographic drag and try to simulate everything with the damping. So I think you have to have more than just the resolution. I don't know the sensitivity directly to resolution. I don't know about that.
All right, so for these different CMIP models, you do have some information about what sort of dynamic capabilities that they have?
I think it's hard to, I think you have to, if you've seen in these models that do best are 3, it's max Planck, so then essentially this is just one model. If you do just 3 different realizations for the max Planck high resolution middle atmosphere model. And then there is the another, but you can also see they have another model. It's the Canadian model that's doing that properly. So, it's to pin that really down what they do. It's I think that really needs to be studied more clearly. What we have done in the past, we have looked at with Tiffany. We looked at the Canadian models with different what you do with the modelet, and that has a strong effect the way how you do this also. Even in a low top model. So there's no. You can do your best, and you have to see what comes out, I guess. So I don't know.
Okay, last question is: do the QBO capabilities, Brewer-Dobson circulation capability of these models have any role in this?
I think it depends. How they. I think for the if they. I don't know if it's the QBO itself affects the representation of this. I don't know. So that's that I don't know.
All right.
Okay.
Thank you.
I don't know.
Craig, thanks for the questions and figuring out how to use the hand raise feature. And make sure you put your hand back down in WebEx. So, Judith, thanks for the presentation. I think we're going to move on to the next presenter now. Thank you.
Thank you.
Okay, and before Ming actually gives his presentation, he did have a question for Larry Horowitz. So I know Larry's in the Smagorinsky room at GFDL, so probably not right by the mic right as I'm saying this, but I just wanted to wait a few seconds and let Larry get back to the mic and then see if he can field a question from Ming before Ming gives his presentation. So I'm talking very slowly to allow that to happen, and I'm going to unmute Ming right now. Ming, are you on the line?
Yes.
Okay, and then Larry, I'm going to unmute your line in the hopes that you're back at the mic now. Larry, are you there?
Yeah, I'm back.
Oh, great. Okay, so Ming, did you want to ask your question?
Yes, about your non-hydrostatic model simulation of QBO. I assume you have to increase the resolution, right? And so in the non-hydrostatic model simulation, do you increase both vertical resolution or horizontal resolution? And which one is more important at the QBO?
For those set of simulations, the resolution was actually identical. It was C360 resolution, which is 25-kilometer resolution in the horizontal, and
okay, thank you.
But it was identical vertical resolution in both.
Okay, that's very good. Thank you.
L48 or something, or 32? L60. 60. The crowdsourced answer here seems to be about 60 vertical levels.
Okay, 60. Okay, yeah, all right. Thank you.
Sure.
Okay, thanks, Larry, and thanks, Ming, for the question. So, Ming, I'm going to transfer control over to your computer now so you can give your talk.
All right.
Okay, I just transferred it, so hit the Share My Desktop button so we can see your screen.
Okay, I did. All right. Should I start?
Yeah, just go full screen with your slides. Okay, looks good. Go ahead, Ming.
Okay, so this is a kind of new research, and part of research also is done with collaboration with the people at the CPC, Hugh Van den Doel, and also the mostly with the student at the FSU. And so here I'm just trying to report the new research opportunity, actually the forecasting opportunity for the cold air outbreak and at a sub-seasonal time scale. And here, I just go over here why we are doing this. So the source of prediction scale is coming from, for weather prediction, really is from the Raspberry wave, volcanic system, and due to chaotic nature, we have the predictability of 1 to 2 weeks, okay? And in the 90s and the last century, and we have used a scale for include the ST called the low boundary 40. This is particularly used for El Nino events, okay, in the tropical ST. And but El Nino does not come every year, and also because of the large variability, internal variability, and even we have El Nino, the forecast is not very decisive, and we have limited scale, even we know the El Nino, like the MAPP type run. And the new source of prediction, we believe that it could come from global mass circulation. In that view, the actual tropics is connected to the tropics, the stratosphere, and the troposphere is connected to the stratosphere with the stratosphere-troposphere coupling. This coupling particularly strong over high latitude, okay, which has a much longer time scale. So here also we want to say here, traditionally for sub-seasonal forecast, we tend to forecast the monthly mean flow, monthly mean temperature anomaly, for example, or seasonal mean temperature anomaly. So cold air outbreak is extreme events, but more frequently extreme events. Every winter we have number of events, particularly like this winters, okay? So it's important to forecast these events, and also the cold air outbreak is more like weather events, not only climate events, extreme events, because we have wintry storm like snow, frozen rain, and high wind, icing, and freezing. This kind of phenomenon, hazards. Okay, and the forecast as a winter storm-related hazard at a longer lead time helps the business and the government to prepare for the threats. Okay, and the business functioning, for society functioning, like school, business closure, road highway snow removal, and rail track de-icing, and also prepare the flight cancellation, and also prepare for the agriculture, potential loss of agricultural products, etc. So here, the thing we talk about is to do this forecast within the model, okay? We are not talking about statistical model, it's a physical-based forecast. So this how we overcome the 2 weeks predicted limits, okay, for weather using NWP model. So first, we needed to have some robust diagnostic relationship between some circulation index and the cold air outbreak. Next, the circulation index that have robust diagnostic relationship with the cold air outbreak can be predictable, okay, or have some scale by the operational model. Okay, so that's something, minimum thing we need to have. So here, I just go quickly review what the typical circulation index that has good diagnostic relationship, but not necessarily have good scale in terms of forecast, by the model, and or by any mean. So, and also the relationship mostly on the monthly and seasonal mean. It does not necessarily reflect the cold air outbreaks. So the one thing is AO index. So AO is negative phase. You tend to have a cold air monthly mean temperature is a cold bias, okay? And the positive phase you have warm bias. And this also has been explained the trend and the inter-annual variability. And another is the stratosphere is called the annular mode or stratosphere southern warming events. And as I say that typically you have a strong negative phase of NAM, or which is corresponding to stratosphere warming events, and you have cold temperature anomaly about 1 to 2 months after stratosphere warming. This signal is similar to QBO, equatorial QBO events in the easterly phase, but it's very drastically different from the ENSO events. So they have different signals. That's the way, as we can say here. And so also, they argue the stratosphere signal can propagating towards the surface at about 20 days, something like this. And that's only strong events can reach the surface. But the question is that we need to forecast this stratosphere signal, and statistically is as difficult forecast as the stratosphere southern warming events, maybe as the cold temperature event as well. So here, and also here the AO index has with cold air surge. Okay, this is a study for Asia, and you see that the positive phase, East Asia, you tend to have warm season mean, and also negative phase has a cold. But if you look at the extreme events, okay, so you see that very strong negative AO is connected to the is connected to the AO, negative phase AO. So very strong negative AO events is connected to the surface cold air outbreak in the East Asia. So here we propose this meridional mass circulation indices and the cold air break. So this is based on the work and one with my student Shen, and this is basically this is more follow up the pioneer work of Dang Johnson's. So basically the circulation from mass circulation perspective is one cell, okay, and the stratosphere cell is connected to the tropical cell. We call it extratropical hot air cell, and the tropical hot air cell and also connected to the extratropical hot air cell. And so here by the Dang Johnson's theory, mass circulation theory, all we need to drive the circulation, meridional mass circulation, is a baroclinic amplified wave, which has a westward tilting. So this wave, by the same wave, okay, this wave would transport net warm air into polar stratosphere and upper polar tropospheres, and also transport net mass from Arctic or polar lower troposphere into the mean latitude. So that's the circulation is connected, okay, and by the same wave, so they are synchronized effectively. So here, this circulation view here, you have stronger circulation. I mean, every day you always have cold air if westward tilting wave, always have cold air going south, or warm air going to north, but the total amount is very small. Both cold air going south and the warm air going north. But have stronger circulation, you have more warm air going north in front of trough, and more cold air going south in behind the trough as well. So those are the periods you tend to have all cold air outbreaks. So here we show the probability distribution, and this has been published in GS. So we show this is you have a stronger circulation, for example, here, and CH is the cold air for high latitude, CM is the cold air for the mid latitude. So when the circulation is weak, okay, you can see circulation is weak, and the probability shifting to the high, very cold in polar region, okay. Meantime, circulation weak, relatively warm in the mid latitude, and even circulation is very strong here, okay. The cold air, high latitude is more warm, and the PDF shifting to the cold in the mid latitude. Okay, so this goes same way. Here, this shows the probability of the cold air events. Okay, so you see that the white color is climatology value here. Okay, in weak circulation, mid latitude has a low probability of cold air, high probability of warm air temperature. Okay, but in the strong circulation case, and the mid latitude have a high probability have cold air. It's very cold. This is compared climatology, lower climatology by half standard deviation. And this is now the warm temperature norm is very, very small. Okay, so there's a big difference, about 20% difference. So remember this event by itself only 30%. So here, this is the key finding here. So basically, let's go back. Variability of mass circulation, a warm air branch is synchronized with the cold air branch. Okay. So here we see light warm air transport in polar region is compounded by the weak circulation in the surface. So stronger circulation, and here stronger warm air into the polar stratosphere is accompanied by the stronger equatorward advancement in the cold air. So this is called cold air outbreaks and warmth in high latitude. So here that's we want to say this. There are two features. One is both continents get cold together. Another is one continent get cold west. Another continent is warmer. So there are two types of cold air outbreak. So here we just show the early study. We show the polar propagation. So why the stratosphere is connected to the troposphere. Due to time limits, I want to skip this part very quickly. So we say that this polar propagation also implies downward propagation. Basically, we are saying the downward propagation is a result of polar propagation. And here, show the CFS model forecast. This is done with Hugh and the people at the CPC. And so this is show the CFS model indeed has good scale in forecasting the polar temperature in stratosphere. So this is for winter season. Okay, you see this is a true scale. Okay, particularly in spring, still have good up to lead time 32 to 40 days. Okay, but this scale we lost all scale in the summer. Okay, come back in the fall, mostly in the early winter and also in the springtime. Okay, and this shows the relative scale with respect to the persistent forecast. You see, this model really is not because stratosphere is long-lasting events or more persistent. Really, the model has a scale. Okay, model is neither dynamics. For example, QBO, the model even have long-lasting persistent time scale. Model could not capture it. But in the polar stratosphere, model can capture it, but only in the winter time. So this is what we see here. Basically, the model, CFS model can capture the circulation and also timing of the warming events 3 to 4 weeks in advance. Okay, and the remark scale comes from the propagation signal. Okay, and captured by the model. And also here we argue, we also prove that the model indeed can capture wave, but the model cannot predict the location of a trough and rate of this wave, but they can capture the amplitude of the wave and the westward tilting feature. This is the reason why we have this poleward mass circulation signal in the model. So here I kind of review due to time limits. I think I want to go, this review was the past year, so I want to skip this part as this show the model in the scale. Okay, in the stratosphere, the model, the last year, first half year is very, very weak event, no event. But the last, starting early of 2014, you see strong events, the model indeed can capture up to day 30 and 40 here. Okay, this is scale. Okay, this is the scale of the model forecast. Okay, remaining scaleful above 0.3 or 0.4 level, even up to day 30. This is the same model, the operational model, okay, CFS V2 forecast model. Okay, so this year we used the last year's experience and also encouraged by the model results. We launched an experimental forecast for cold air outbreaks in real time. So we have a website, and you're welcome to look at the website, and your feedback and comments are appreciated. So what we do, we do the weekly forecast every week, and we try to forecast the events 30 to 40 days in advance. Okay. So here, that's kind of a procedure. We use the model of output derived from the operational safety model in real time, and as reference plus forecast knowledge. So in other words, the model forecast is not far from perfect. We need a human knowledge, and basically it's a human forecast. Okay, and once with this, we use diagnostic relationship between the stratosphere and the surface, the cold air outbreak, and do this forecast for the cold air. So products, we issue the forecast about the time periods of strong mass circulation events plus likelihood of cold air outbreaks. Okay, so just about the time, not the intensity, this thing here. So far, we made 14 forecasts. None of the forecasts false alarm. They're all accurate, and they all produce events. So 12 of them have already happened, okay? And 2 is one, the current one, the cold air outbreak, is we forecast the 13th one, okay? We first issued that forecast February 12th. We forecast to occur in March 12th to 17th. The peak was yesterday, so that is the last day of our window period, okay? And they have another peak and in the few days later. So also we forecast another events, the upcoming events, which on the February 18th to occur in the last few days of March and the first few days of April. This is probably the last event we're going to forecast, because by that time we don't have the skill in the stratosphere anymore. So average lead time of this forecast, all the forecasts, about 30 days or longer. Okay? And all the forecast stratosphere are associated with cold air break. That's remarkable too. Okay, and by itself, except one event, I think they have minor cold air break, which are on January 18th. So we actually cover total 31 round cold air outbreak. Okay, we include with this event. Probably we only miss 8 cold air break events. Okay, because the stratosphere signal is very weak, but this cold air break only associated with the cold air tropospheric circulation. That's the reason we could not forecast. But nevertheless, they are only a few days later after the cold air break we forecast. Here we gave this kind of slides showing here. So maybe I just highlight a few of them. This is events, Halloween events. We forecast 30 days in advance. Okay, this is another one. Maybe the strongest event here is in the New Year. We forecast on the 11th November 20th. Okay, and this is the mark of the cold air, okay? And how this is temperature area index. So each peak here is cold air outbreak. Okay, that's how we forecast. And here this is another event. This is a New Year event. I think another event, stronger event is around this February 18. Okay, that's I think many northeast part of the country has a record-breaking temperature, cold temperature. We focus on the January 10th. That's the target date is February 13 to February 18. That's the date of occurrence. So this is a very successful forecast too. Okay, and plus this is what's happening now. Okay, and they call stratosphere J events. So that's the cold air outbreak associated with each of them. Okay, and here I just say that we know in the next phase we try to take the extent. We know the route of cold air, so we try to link this route of cold air with the events, so we can actually produce a map of cold temperature and anomaly 30 days in advance as a forecast. So here, this conclusion, we do have our opportunity for new forecasts. This is a forecast of cold air outbreak branch outbreak events is built on the intrinsic connection between the amount of air mass transport into the polar stratosphere and the occurrence of massive continental scale cold air outbreaks. Okay, and the numerical model like NOAA CPO is indeed capable of predicting the amount of mass transport the polar stratosphere with timing information in this good scale at a time longer than 1 month. Okay, although it cannot do so for tropospheric circulation. Okay, and the combination of both factors leads to a unique opportunity for the hybrid forecast. We call it dynamic plus statistical strategy that allow us for the first time to predict occurrence of massive cold air outbreaks 1 month ahead. That's it. Thank you.
Great. Thanks a lot, Ming. Any questions for Ming, please use the hand raise feature in WebEx. Ming, I'll just wait a few seconds to see if anybody has anything. Okay, Ming, I'm not seeing anything, and since we're a little bit past 3, I think we'll adjourn now, but thank you so much for presenting.
Okay, thank you.
Okay, so thanks to all 3 of our speakers, and thanks to those who dialed in today. I think it was a very interesting webinar. We have 2 webinars coming up in May. We're not going to have one in April at the moment, but stay tuned to the website in case. In May, the webinars are going to both be focusing on the efforts to transition research into various applications, particularly operations, with a focus on NCEP. And the first one is going to be on May 7th, and it's more of a programmatic talk. It'll talk about some of the organizational efforts. So we're going to hear from Anarita Mariotti, who's the director of the MAPP program here in CPO, and Jin Huang, who is the director of the climate testbed at CPC, and also Hendrik Tolman, who's the director of the Environmental Modeling Center at NCEP. And then the next week on May 12th, which is a Tuesday, we're going to hear a little bit more about the science and the actual working efforts on transition. And so we're going to hear from Sarah Liu, who's at the University at Albany, talk about some of the aerosol work she's doing. Mike Eck, who's at the Environmental Modeling Center, is going to talk about some of the land model implementation they've done there. And then Cecilia DeLuca, who's out at the Earth System Research Laboratory, and she's going to talk about some of the infrastructural issues related to implementing new modeling code. So I hope that everybody will be able to join us in May. Please take a look at the MAPP webinar website. There will be a recording of this webinar up, hopefully within the next 24 hours, as well as the slides. So thanks everyone for joining, and thanks again to Ming, Judith, and Larry for taking the time to present.